Good morning. This morning we're going to discuss the heat exchanger design process. There are no hard and fast rules for design, but these are general guidelines that I hope will help you in your heat exchanger design process. So I want to start over here with just some general guidelines. So this is an outline of everything that I'm going to talk about today. In the heat exchanger design process, we start out by identifying the application, and by that I mean we need to determine the temperatures of the whatever flows we have, the heat loads, meaning the Q, the mass flow rates, and anything else that might be important. The second step in the process is to decide on the construction type. We have a variety of types that we can choose from. Once we've done that, then we'll evaluate the log mean temperature difference. We'll determine Q if we haven't done so already, and then if we need to, we'll get a correction factor that we can use to determine Q. Then we'll decide on the dimensions. Once we pick some dimensions, we'll evaluate the heat transfer coefficient on the hot side of the flow. Then we'll evaluate the heat transfer coefficient on the cold side of the flow, and then we'll determine the overall heat transfer coefficient. Once we've done that, then we can determine to see if our dimensions were correct. Usually they're not, so we have to go back and iterate to get the correct dimensions. And then finally, we want to check the power consumption. And the power consumption I'm referring to here is the power that's required to there's required to get the flow to go through the heat exchanger, not the power for the heat itself. Okay, so first of all, let's go through the identify application process. And I've drawn a little diagram here to help you with that. So at this point, we really don't have the type yet. In this case, we just have a heat exchanger where we have cold flow coming in, hot flow coming in. And so in this particular case, it's been specified for us. The inlet temperature of the cold flow is 35 degrees. The outlet temperature is 120 degrees Celsius. The inlet temperature of the hot flow is 300 degrees Celsius. And the outlet temperature of the hot flow needs to be 150 degrees Celsius. The mass flow rate of the cold water is 2.8 kilograms per second, and the mass flow rate of the hot water is 1.4 kilograms per second. Okay, now that we've identified the application, we want to go to step 2, and that's decide on the construction type. So we have to pick something. So based on just the application, we don't know what to pick, so we just, based on our experience, we'll decide, okay, in this particular case, I said, we're going to use a shell and tube heat exchanger, and I've drawn that here, just a diagram. It's going to be shell and tube heat exchanger with a single tube pass. Okay, how did I know to choose a shell and tube heat exchanger? Well, I really didn't. I just had to pick one. If I were doing this for a real application, I would say, okay, well, what have other people used? What do I know from my experience? And so forth. And the way you get experience is just do more and more of these. Okay, so we picked the shell and tube with a single tube pass. Okay, with the shell and tube, we have a tube bundle within a shell. We have an inlet header, and that's where the tube flow would come in. They pass through the tubes. It's a one pass, so they just go through one time, and they come out through the exit header down here. And here's our tube bundle down here. And then I've shown baffles, so we'd have flow coming in like this for the shell flow. Okay, so now we've decided on the construction type. The next step would be to determine the log mean temperature difference, the heat rate, Q, and our correction factor. So I'm going to go to the board now. So in order to get the log mean temperature difference, well, first we need to determine Q. Okay, Q is given by m dot Cp delta T, and we can choose either the hot flow or the cold flow. And they'll both work. I've chosen the cold flow here. We need to evaluate the specific heat. To do that, we choose the average temperature, which would be the average between T cold out and T cold in, and it's 350.5 K. So I look that up in the back of the book, and I get CP is 4195 joules per kilogram K. So we can plug that in. For our cold flow, we had 2.8 kilograms per second, and our temperature out was 120, temperature in was 35, and we get a Q of 998,410 joules per second, although we normally express this in kilowatts, so that would be 998.4 kilowatts. The next step, then, is to determine the log mean temperature difference. And if we're going to determine the correction factor for this flow, or any type of shell and tube heat exchanger, we need to know the log mean temperature difference, and we're going to get that for a counterflow situation in a parallel pipe heat exchanger. So to get the log mean temperature difference, we have to get delta T1 and delta T2. So delta T1 would be T hot in minus T cold out, and we plug in the temperatures and we get 180 degrees C. Delta T2 would be T hot out minus T cold in, plug in the temperatures, and we get 115 degrees C. Then our delta T log mean, we can look that up in chapter 11, and we find that it's delta T2 minus delta T1 over the log of delta T2 over delta T1. Plug in the numbers, and we get that the log mean temperature difference is 145.1 degrees C. All right, the next step is to determine our correction factor. All right, so I want to go over here, back to the overhead. And we're going to use this table that was part of the handouts that I gave out. Okay, and over here on the vertical axis, we have our correction factor F. On the horizontal axis, we have what's called P. And you can see it's P, it's a little formula is given here. P is equal to little t out minus little t in over big T in minus little t in. And then over here, these pink lines or magenta lines, we have R, and that's given by big T in minus big T out over little t out minus T in. So we need to calculate R and P so that we can use that graph. So I've done that on the board over here. All right, and it says on the table, which you couldn't see here, but if you look in the notes I gave you, it's on there. The little t's are the tube side flow, the temperature of the flow that's going through the tube, and the big T's are on the shell side. So if we calculate P, plug in the temperatures, we get 0.566, and if we calculate R, we get 0.567. So we go back to the table here, and we have P is 0.566, so we go to this point right here on the horizontal axis, and then we go up to R, which is a pink line, which is where it's 0.567, and if we go up until we hit the line that's 0.567, we get right about here, and if we come across, we get an F of 0.93. So I've written that on the board over here. Okay, so that's our correction factor. Okay, the next step is to determine the tube bundle dimensions, because we have a shell and tube heat exchanger, we've got bundles. Okay, so I have another diagram over here to show you the bundles. Okay, now if we look at this, I've chosen 4 rows of tubes. So we have 4 rows. You can't see it. There we go. We have 4 rows of tubes, and there are 8 tubes per row. Okay, again, I did not know exactly what to choose. I just picked a number. Okay, the flow is coming down in this direction like this. So we have flow coming into the tubes. That's the tube side flow. And then the flow over the tubes is coming down like this. Okay, now we can choose the tubes to be staggered or aligned. The next step will depend on whether we choose them staggered or aligned. I have a diagram for that. right here. Okay, so we have two choices. First would be the aligned configuration, and you can see that in the vertical direction they're aligned, and in the horizontal direction they're aligned. And we have flow coming into the tubes like this. So V infinity would be the velocity of the flow far upstream of the tube bundles, and T infinity would be the temperature far upstream. Okay, we have four important dimensions here. We have the diameter of the tube over here, and then we have ST, which stands for the transverse pitch, the distance between the center lines in this direction of the flow, and then we have the longitudinal pitch, which is the distance between the center lines in the direction of the flow. And then finally we have the area between the tubes. Okay, if we chose a staggered configuration, it would look like this. So we have this row, in the vertical direction here, they're all aligned, but in the horizontal direction, you can see this row is offset. So again, we have V infinity far upstream, T infinity far upstream. We still have our transverse pitch, and we have our longitudinal pitch and our area, but I've added two additional dimensions. One is the diagonal pitch, the distance between the center lines of two tubes in different rows, and then we also have a second area. So we have the flow will be going through area 1, but it will also have to go through area 2, and that will make a difference in our calculations. Okay, so now that we have that, we can use that to calculate our Nusselt number. So we have external flow over tubes, so we're going to pick the appropriate correlation. This is the one that I chose. The Nusselt number is equal to 1.13 times C1 times the Reynolds number based on the maximum flow velocity, not V infinity, but the maximum flow velocity in the tube bank, raised to the m power Prandtl number to the 1/3. If you're using the 6th edition of Crepera and DeWitt, that's equation 760. Okay, and the restrictions on this correlation, the number of rows, NL is the number of rows. The number of rows has to be greater than 10. The Reynolds number, based on the maximum velocity, has to be greater than 2,000 or less than 40,000, and the Prandtl number has to be greater than or equal to 0.7. All the properties are determined at the film temperature. Whenever you have a correlation, if you read the paragraph before and after, it'll tell you what conditions to use to calculate the properties. And the film temperature is given by the surface temperature of the tubes plus T infinity divided by 2. And then we have a couple of constants here we have to deal with. We have C1, which can be obtained from the table in the book, as can M. That should be M right there, I believe. Let's change that to an M. Okay, now it's possible we could have, this should be a less than, it's possible we could have less than 10 tubes. So if we have less than 10 tubes, we can apply a correction factor. The correction factor, the Nusselt number, if we have less than 10 tubes, would be the Nusselt number that we calculated for 10 or more tubes times C2. C2 is given in a table. If you have the 6th edition of Crepera and DeWitt, you can find it there. Okay, the next step is we need to find out what the maximum velocity is so that we can calculate the Reynolds number in our Nusselt equation. Okay, we have, first the Reynolds number is based on the maximum fluid velocity occurring within the tube bag, not V infinity. So let's talk about the aligned tubes first. Okay, if from the aligned tubes, if you refer to your diagram, from continuity, V infinity times ST also has to equal V max times ST minus the diameter. So we can solve for the maximum velocity, and we have ST over ST minus D times V infinity. So if we have aligned tubes, this is the velocity we're going to use in the Reynolds number to calculate the Nusselt number. Okay, now let's discuss the staggered arrangement. For the staggered arrangement, Vmax could occur through either A1 or A2, whichever is smaller. So let me go over here and I'll demonstrate what I'm talking about. We have the flow coming in, and you can see this would be A1 here. It could go through here, but it's going to make a turn here and go up through A2 right in here. Now when it makes the turn, if you notice, the flow comes in, it goes through this one area, but when it makes the turn, it goes through A2 over here and another A2 over here. Okay, so we have flow through A1, which is right here, then it bifurcates, part of it goes over here, part of it goes over here, and we have to take that into consideration. The way we do that is, if we look at the board, we have from continuity, V1A1 equals V2 times 2A2 because it has to go through two A2s. Okay, so now we need to know which one is larger, V1 or V2. Well, we know that V1, so we can rearrange it. We have V1 over V2 is equal to 2A2 over A1. And then if we plug in those dimensions, we have 2 times L times SD minus D over L times ST minus D. So we cancel out the L's, we're left with this expression. V2 is greater than V1 if ST minus D is greater than 2 SD minus D, or if we rearrange that, if SD is less than ST plus D over 2, then V2 is greater. So if this is true, what we just said, then Vmax would be ST over 2 SD minus D times V infinity. If that was not true, then the other V is the max, and it occurs at A1, and so we would use this expression, ST over ST minus D times V infinity, just what we have for the alarm tube. Okay, then once we have Vmax, then we can go back and calculate the Nusselt number. Now sometimes it turns out that the correlation that I gave you just previously for the Nusselt number may not apply. There's another correlation that you might be able to use which extends the Reynolds number range, and that's this correlation right here, which in the 6th edition is equation 7.64, and if you have a different edition it might have a different number, but you could find it. And it's equal to C times the Reynolds number based on the max velocity to the m power, Prandtl number to the 0.36, and then we have this expression, Prandtl number over Prandtl number S to the 1/4. So this would be the Prandtl number of the flow. This would be the Prandtl number evaluated at the surface, all raised to the 1/4 power. And then we have the conditions. The number of rows has to be greater than or equal to 20. Prandtl number between 0.7 and 500. And the Reynolds number we can drop all the way down to 1,000 and go out to 2 million. Now this one, all the properties are evaluated at the arithmetic mean of the fluid inlet temperatures. And C and M are listed in table 7.7 in the 6th edition. Okay, if the number of rows is less than 20, just like before, we can apply a correction factor. The Nusselt number, based on the number of rows, if the number of rows are less than 20, is equal to the Nusselt number that you calculate for greater than 20 times some correction factor, C2, and C2 is given in table 7.8. Okay, now that we've done that, we need to pick some dimensions. We don't have any dimensions yet, so why don't we go over to the overhead here, and we've got to pick something, so we don't know what to pick. We'll just have to pick some numbers and see if they work. If they work, then we're okay. If not, we'll just iterate on the process. Okay, so what I've chosen is a staggered design. We have flow coming in from the top, so I'll put our dimensions on here, and then I've just chosen some dimensions down here at the bottom. I said we'll pick a diameter of 19 millimeters, a longitudinal pitch of 29, and a transverse pitch of 29, and we'll just see if that works. Okay, so having done that, we'll come over here, and we also, from those dimensions, we can calculate the diagonal pitch, and so we just use the Pythagorean theorem, and we get SL, this is the square root of SL squared plus ST over 2 squared, and plug in the numbers, and we get SD, or the diagonal pitch, is 32.4 millimeters. Okay, the next step is to evaluate the heat transfer coefficient on the outer tubes. So let's look at a diagram first to see what we're talking about. If we look at the shell and tube heat exchanger from the side, what I've drawn here is, you know that we have flow going through the tubes like this, and then from the side we have cross flow. So it's coming down like this. We put 3 baffles in here. We come down, the flow goes down, then it turns and it comes back up and it goes across like this. Now these dimensions are going to be a little hard to see, but I want you to notice this BF is the dimension from here to the first baffle and then to the second baffle. So the length of this whole shell here is 4 times BF, and that's going to be important in a minute here, so we want to note that. Okay, now if we look at the flow as it's coming down into the flow like this, we have the tubes, the flow is coming down into the tubes, but notice I put BF over here. So this is the length of the tube within the baffle. Then the width, the overall width of the heat exchanger is I've chosen it to be ST, which is the transverse pitch, you know, the distance between these 2 tubes. So that would be times N, but I've added an extra 2 here to take into account space at the end here. So rather than having this tube right up here at the wall, we put some space here. So this +2 right here gives us some extra space at the end. So that's the width of it. So within each chamber, the cross-sectional area is BF times the W. Okay, so let's go to the board now because we need to calculate Vmax. Okay, so first of all, the width, we've already chosen the transverse pitch is 29 millimeters. So the width of it then is going to be ST times N plus 2, and we calculate that, and it ends up being 0.29 meters. BF, we don't have a number for that, so that's part of our design procedure, and we just have to do the best we can. We'll just choose BF to be 2/3 of the width. It just seems like a nice number, so we chose it to be 2/3 of the width, and later on we'll go back and check it and see if that's going to work. And so if we multiply that out, the BF ends up being 0.19 meters. So that means the flow area is then going to be BF times W, and so we calculate that, and it's 0.0551 meters squared, and now we can get V infinity. Okay, so this is the flow velocity approaching the tubes, and that's just equal to the mass flow rate times over rho A. So we plug in our numbers, and we get V infinity just happens to have, it's 0.051 meters per second. So that's coming into it, but we're not going to calculate the Reynolds number based on that V infinity. We have to find out what Vmax is. So we still need Vmax. Okay, now we've chosen a staggered arrangement, so we have to ask the question now, is SD less than ST plus D over 2? So that we'll know which Vmax to use. So we plug in SD here, we plug in our numbers, and it says, the question is 32.4 less than 24? Well, obviously the answer is no, so then we go back and choose our other alternative. Vmax ends up being ST over ST minus D times V infinity, and so if we calculate it, we get the Vmax. I don't think you can see it. All right, Vmax is, here it comes, Vmax is equal to 0.148 meters per second. All right, so now we can come over here and we can calculate the Reynolds number based on that maximum velocity. So the Reynolds number on this board is equal to rho Vmax D over mu. So we look up our properties for kinematic, or for the viscosity. We plug in our numbers, and we want to make this cancel out. So we have a Newton here, so we have to put in a unit fraction here. A Newton is equal to kilogram meter per second squared. Okay, so the second squareds cancel out. We have kilograms cancel out. That meter will cancel out that meter. And then we have meters. That will turn that into a squared. That cancels that. The Newton cancels that, and I didn't cancel that one. So we end up with a dimensionless number, and RED max ends up being 7704. So I chose to use this expression for our Nusselt number. All right, we need C1 and M and C2 in order to get the Nusselt number. We just discussed that previously. So in order to get C1 and M, we go to table 7.5 in the 6th edition, and we look under staggered flow, and we have to calculate SL over D and ST over D. It turns out they're the same. They're both 1.53, and so we look it up, and we get that C1 is equal to 0.46, and M is equal to 0.562. All right, but because we have less than the required number of tubes, we have to get the correction factor for C2, so we go to table 7.6, and from there we can find that C2 is 0.89. So now we're ready to calculate our Nusselt number. So we just plug in all the numbers, 0.89 times 1.13, so forth, and we get a Nusselt number of 93.0. And then once we have the Nusselt number, we know we can calculate H, which is going to be the heat transfer coefficient, and we plug in our numbers, and we end up with an H of 3277 watts per meter squared K. And that's the heat transfer coefficient for the outer tubes, on the outside of the tubes. And we're going to use that later to calculate the overall heat transfer coefficient. Okay, now we're ready to move inside the tubes. We need the heat transfer coefficient inside the tubes. Okay, so we're going to evaluate it. We need the mean velocity inside each tube. Now it could be a little tricky here. The mean velocity of the tube is equal to mass flow rate over rho of water times the area of the tube, but we've added in this extra term here, N. Okay, it's not the total mass flow rate, it's the mass flow rate through each tube, so we have to divide by the number of tubes, so don't forget that. So N is the number of tubes, and so what we end up with is the mean velocity inside each tube is equal to, well, what I've done is, instead of plugging in the density of water, I've left it over here because I know I'm going to use it in just a minute in the Reynolds number, it'll cancel out. So I've written the mean velocity like this, 154.3 kilograms per second over meters squared divided by the density of water, and you'll see why in just a second. You don't have to do this, it just is a little more convenient. It's one less thing you have to calculate. And of course we evaluated at the mean temperature of 98 K. Okay, so now we're ready to calculate the Reynolds number inside the tubes. So we have density of water times the velocity, and so see we have the velocity includes density of the water, so that cancels out. So I never really needed the density of the water. And then we had newtons. For the viscosity, we had newtons here, so we have to multiply by this unit fraction here. A newton is a kilogram meter per second squared, so the newtons cancel out. We have a second squared cancel out. Kilogram goes away. These meters squared go away, and a meter here. So we're left with a non-dimensional number of 24845. Now that we have that, we can calculate the Nusselt number for internal flow. We can use either equation 859 or 860, and that's in the 6th edition. If you have a different edition, it might be a different equation, but you can look it up. And the Nusselt number is equal to 0.023 times the Reynolds number to the 4/5 times the Prandtl number to the n power. Okay, and that's equal to HD over K. So we can calculate the heat transfer coefficient, plug that in, and we get the heat transfer coefficient ends up being 2438 watts per meter K, and that's inside the tube. And we'll use that in just a minute to calculate the overall heat transfer coefficient. Our next step is to determine the overall heat transfer coefficient. So we'll use the equation that we've learned in class, 1 over UA equals the sum of the resistances. But before I do that, I'm going to make a few assumptions. First of all, I'm going to assume that they're thin walls so that the inner diameter of the tube equals the outer diameter, and therefore the inner area equals the outer area of the tubes. And second, we're going to assume that there's no fouling in a foot play. So that allows us to reduce the equation to 1 over UA equals 1 over H outer A plus 1 over H inner A. The A's cancel out, and so we can just plug in the heat transfer coefficients that we calculated. For the outer, it was 3277. For the inner, it was 2438. So we add them together, and then we take the inverse, and we get the overall heat transfer coefficient is 1398 watts per meter squared K. Okay, now that we have that, we're now ready to determine the dimensions, and the dimension would be the of interest here is the tube length. How long does the tube have to be to accomplish this heat transfer? So we go back to the very beginning. Remember, we wrote that Q is equal to UAF log mean temperature difference. Well, we have all these terms now, except for the area. So Q is equal to U. The area is equal to the number of tubes times the heat transfer area of the tube. So that'd be pi times the diameter, that's the circumference, times the length of the tube. And then we've already calculated F, and we have log mean temperature difference. So we can rearrange that and solve for L right here. We plug it all in, and we get that the length of the tubes has to be 2.77 meters. So now we have our length of the tubes. Okay. Now we haven't said anything about how many baffles we need, so we have to determine the required number of baffles. Remember, I drew it up there with 3 baffles, but we never used that number 3, so we don't know if that's the right number of baffles. Okay, recall that within each section, the length of the baffle was BF. Remember we did that? Okay, well, if we take the length of the heat exchanger, this overall length L, which we just calculated as 2.77 meters, has to be divided into these sections. Okay, so for example, if I have 3 baffles like we started with, then the total length has to be this L here, which would be BF times 4. Okay, so now we can come over here and calculate the required number of baffles, and we can use this equation. M is the number of baffles, so the number of baffles would be the total length divided by BF minus 1, because we have one more section than number of baffles. And remember, the baffle BF was 0.19 meters. We calculated that. So M, the number of baffles then, is 2.77 divided by 0.19 minus 1. We end up with 13.6 baffles. Well, we have to have a whole number of baffles. This is not going to work. We don't have the right number of baffles. So what we're going to have to do is going to go back and iterate. So we chose BF to be the wrong number, so we have to go back to that step again. We have to go all the way back to that step and pick a different number for BF. Now, if you're careful and smart about how you set up your spreadsheet, then all you'll have to do is go back and change this number, and hopefully everything will flow through, and you just keep changing BF until you get a whole number for the number of baffles. Okay, once we have the number of baffles, then everything is set. We've got our heat exchanger design. We have all the dimensions we need. There's one last thing we have to do, and that's step 9. We have to check the power consumption to see if what we've designed is actually practical. We've got to get that flow to go through the tubes. We could pack those tubes so closely together, we get great heat transfer, but we might not be able to force the flow through. So we have to check the power consumption, and we're talking about the power consumption that it takes to force the flow through the tubes as well as through the shell. The power required to do that is given by this expression here, the volume flow rate times the pressure drop through the tubes. We can get the pressure drop through the tubes using figures 713 and 714 in the 6th edition, and of course it might be a different number if you have a 7th edition or a 5th, but it should be obvious. So once we have that, we can see how much power is required. If the power required is some practical number that we can accomplish, then we're done. If the power required is some huge number that's impractical to accomplish, then we're going to have to go back and start over and probably have greater spacing between the tubes or something like that. So I just want to recap the design process now. So we'll go back over here to the overhead. just to remind you of what we've done. Okay, remember, we started by identifying the application. That was to get the mass flow rates, temperatures, anything else that would be specified, heat loads and so forth. We decided on the construction type, and in this case, we picked the shell and tube, but you might pick some other kind of heat exchanger. In our case, we evaluated the log mean temperature difference. We got the heat rate, and since it's a shell and tube, we also needed a correction factor. If you have a different type, you might not need the correction factor. Then we determined the dimensions, and this is something that just is based on experience and judgment. If you don't have that yet, you just have to pick some numbers and develop your experience. So we picked some numbers and plugged them in. Then we evaluated the heat transfer coefficient on the hot side of the flow, and we evaluated the heat transfer coefficient on the cold side. In this case, we made the assumptions that we had thin walls and no fouling, and we were able to easily determine the overall heat transfer coefficient by summing the resistances. Once we'd done that, it says determine the dimensions, and the only dimension left for us to determine was the length in this case. It turned out that the number of baffles based on our process was not a whole number, so we had to iterate until we do get a whole number, and then finally we check the power consumption. So again, in the design process, what I've given you is not a set of instructions. I've given you a set of guidelines, and you can use these guidelines and adapt them to any type of heat exchanger. Some of the procedures will be different for other types of heat exchangers, but it should give you some insight as to how you go through the design process. So thank you very much.